Hello physics fam, we want to now tackle the idea of parallel circuits. So let's go. We've already talked about series circuits, which is where electricity has only one path to flow through. Unlike series circuits, parallel circuits have more than one path. So electricity could flow through this resistor, or if for some reason something happened with this resistor, electricity also has this pathway to pass through. So if this is the negative end and this is the positive end, we see that electricity has more than one option to pass through, to go from the negative to positive end. Because of that difference, we are going to see some differences in how we calculate current and resistance as well. So let's jump into it. To officially define a parallel circuit, let's take a look at these circuits and schematic diagrams. If you take a look, here is your battery pack, and notice that this light bulb has the possibility for electricity to flow to the negative and positive end, but so does this light bulb. Electricity is connected to the positive and negative end. That means that they're both, in a way, each individually hooked up. So that means that if for some reason this bulb was unscrewed and electricity no longer flowed through this little branch of the circuit, this light bulb would still shine bright because it would still have that connection of the positive and negative end of the battery. When looking at this circuit through a schematic diagram, we clean it up a little bit so it's easier to see, because this picture right here, what the circuit really looks like, isn't as easy to see. So we make it a nice rectangular wire. Electricity goes through the first light bulb, and then electricity goes through the second light bulb. Again, that idea that electricity has more than one path is what creates and makes it a parallel circuit compared to a series circuit. Here is an example of a 3 light bulb system in parallel, meaning that electricity from the battery can flow through light bulb 1, light bulb 2, and light bulb 3. If for some reason light bulb 1 and 2 break, 3 is still going to get that electrical energy in order to flow through to light up that light bulb. So we've talked about how the light bulbs would still light if the other ones went out in a parallel circuit. And the reason for that is each device, meaning light bulb, resistor, whatever, is connected to the same 2 points. And that 2 points happens to be the positive and the negative end of a battery. So they each are individually hooked up to the positive and negative end. Now the battery itself might not look like this, but no matter what kind of battery, there's always going to be a positive and a negative end. And the reason for that is you have to have potential difference. You have to have a difference in charge for electrons to go from one level of energy to a lower one. Otherwise electricity wouldn't flow. So because they each are connected to the same 2 points though, voltage is going to stay the same throughout. So unlike in a series circuit where the voltage drops with each light bulb, here voltage is the same throughout. So whatever the voltage is of the battery, you're going to find that that's going to be the voltage in each resistor or light bulb. Okay, so that's one main difference between series and parallel. So make sure you write that down. Voltage is the same for each light bulb or device in a parallel circuit. Now because each light bulb is individually hooked up to the positive and negative end of a battery, that means that each individual resistor will have its own unique current associated with it. So unlike a series circuit where the current is constant throughout because all the electricity gets backed up by the slowest resistor, so everybody is waiting for the electron in front of them to move. Different story when we have a parallel circuit, because again, if we have the option of another hallway, here's a resistor, and here's a resistor, and here's our battery, electricity can flow here, meaning this has a certain current of electricity because of it's a resistor, and the electricity can flow through here as well. So they're each independent of each other. That's an important concept. Since we talked about the fact that each individual resistor has its own unique current, if we wanted to find the total current, we would simply add up all 3 individual currents to give you the total current. And once you had that, right, we could plug that in to our Ohm's law to help find other things. But that's important. So your total current is equal to the individual currents added up. If you take a look at this little picture over here, it says the current outside the branches is equal to the sum of all the individual branches. So if this resistor has 3 amps, this resistor has 5 amps, and this resistor has 6 amps, those are all individual currents for each light bulb. But when added up, that totals a current of 14 amps. So unlike a series circuit where you get caught up with it, the slowest hallway slows everyone down, that doesn't matter. If this is the lowest current, this first resistor here, and it's slowing everyone down, if there's a backup here, they can go through the faster hallway here or here. It's just like when you're in school. If a hallway's jammed, chances are you probably have another hallway option you can use in order to get to class. Same thing with parallel circuits. So that's why all these individual hallways added up for electricity to flow through end up giving you the total current. That's why we have this equation right here. Total current is all the individuals added up. Besides that, we also want to look into total resistance. Now, this equation is simple to do, but don't forget, it's not completely just a set equal to problem. What it is to simplify it, all the inverses of each resistor, so if each resistor, you take the inverse of their resistance, then it equals the inverse of the total resistance. So when we start solving these, you're going to have to be careful because you're setting it equal to the inverse of the answer. So once everything's done, you're going to have to flip-flop your total resistance in order to get the answer. Let's look at over here at the side as an example. You have 3 resistors in parallel right here. Each one is 6 ohms, okay? So if we want to find the total resistance, my equation is the inverse of the total resistance is equal to the inverse of each individual resistor. All right? So that means each one is 1/6 plus 1/6 plus 1/6. That ends up giving you 3/6, which is 1/2. But that's not your answer. The total resistance isn't 1/2. That's the inverse of it. So what you need to do is flip-flop both of these to make it RT on top, or total resistance, is equal to 2. That's where we got this number from for the total resistance is 2 ohms. You took the inverses added up and then you flip-flopped it, and then you ended up with the proper 2 ohms of resistance. Let's try this other one here just in case, right? So you've got 3 light bulbs, each 9 ohms of resistance. So that means the total resistance, which I set equal to the inverse here, is 1/9 plus 1/9 plus 1/9. Well, that is 3/9 added up, which ends up being 1/3. Check your fraction work if you're not following me here, all right? But that is equal to the inverse of the total resistance. So now we have to invert both numbers so that total resistance is on top, but now 3 goes on the top, so your total answer is 3 ohms. Hence, where the 3 ohms came from. All right, if you're still not following, take a look and pause the video and try this out with the new equation and make sure you get 4 ohms. If you don't, then you're not quite understanding that that equation that we just talked about. Okay? Try it out. All right, last but not least, let's take it home. Let's try out a parallel circuit, okay? So we have a 3-battery system set up in parallel with a total voltage of 6 volts. Now remember, we know since each resistor is individually connected to the batteries, because there's other hallways for the electricity to go, it's like they're directly connected to the positive and negative end. So if the total voltage is 60 volts, we can assume that all the individual voltages are 60 volts as well. Remember, that's different than a series circuit where we could guess, or not guess, but imply that the current is constant throughout. Not the case here. Current changes, but voltage stays the same. So that will be important to consider. All right, let's think about the total resistance and solve for this. Remember the total resistance, which by the way, RT, total resistance, is the same as REQ, which stands for equivalent resistance. But let's figure that out. the inverse of total resistance, or equivalent resistance, is equal to the inverse of all three of these resistors. So 1 over 17 plus 1 over 12 plus 1 over 11. When I throw that in my calculator, I end up getting a nice decimal that is about 0.233. Now remember, that is just a decimal, like being over 1. But since we are equal to the inverse, we need to invert both of those numbers. So now RT goes to the top, and it becomes 1 over 0.233, which in turn, the inverse is then going to equal 4.29 ohms. So let me write that down, and let me put that in my actual answer, 4.29 ohms. So now we have total resistance and the voltage on each individual light bulb. Next, we can find either the individual currents or the total current. Let's start with the total current, since that's less work and I don't have as much room here. To find the total current, we want to use Ohm's law, V equals IR, but we want to use the big totals. So the total voltage we know of the system is 60 volts. We're trying to solve for the total current, so we'll leave it as that. And we want to use the total resistance for this problem, since we're finding total current, which is 4.29. If you put that into works, divide by 4.29 to both sides, sorry for the overlap, you end up getting about 13.98 amps. So I'm going to write that over here since I ran out of room. 13.98 amps. All right? So we're plugging away. We know the total resistance, total current, and the fact that voltage stays constant throughout in a parallel circuit. All right, so the last thing we need to do is find out the individual currents on each light bulb. So I1, I2, and I3. And if you've seen me do problems like these before, I like to line them all up at the same time. I think it's easier to set them all up at once instead of individually. I feel more efficient. But again, you certainly don't have to. Now, the resistance on each individual light bulb is different. So let's see here. Voltage we know is the same for all of them, don't we? It's 60 volts. So I'm going to put a 60 for all of these equations. Easy peasy. Now, I don't know what my current is on each one, so I'm going to drop down my I. And I do know the resistance for each one. Light bulb 1 is 17 ohms. Let me put 17 in there. Light bulb 2 is 12 ohms for the resistance, and light bulb 3 is 11 ohms. By the way, if you don't know that ohms is resistance, this becomes complicated, right? You don't exactly know what your Ohm's law is looking for, but R is resistance, and resistance is measured in ohms, that omega symbol that looks like a horseshoe. So if you don't know that, then yeah, things can get a little bit tricky. But since you should know that, let's just divide both sides by the resistance, resistance, and we should be able to determine what each individual current is. Now, spoiler alert, right? All the individual currents should end up equaling what number added up? That's right, the total current. So after we find the answer, we're going to double check and make sure it adds up to about 14 amps, which is really close to 13.98. So I'm going to crack out the calculator here and then put in my numbers. Current number 1, after putting 60 divided by 17, is going to be about 3.52 amps. Looking for number 2, light bulb number 2, 60 divided by 12 ends up being a nice 5 amps. And then number 3 is 60 divided by 11, which ends up being about 5.45 amps. Now let me add 5.45 plus 5 plus 3.52, and it ends up being about 13.97, which is good. It's very close to the total current that we calculated. So in the end, all these individual currents that we know, since they're their own individual little hallways, some might be slower than others, but when you add them all up, all three currents should end up equaling the total current, which is what we talked about. All right, so we introduced parallel circuits today. We talked about how voltage stays constant throughout because all the different hallways end up really connected to the battery still, the positive and negative end. So voltage stays the same throughout. We know that current is different at each step of the way, and that's okay. We can find that individually, and when we add all of them up, they end up equaling the total current. And then for resistance, each resistor, individual one, is different, but added up, we have to use that equation where we take the inverse of the total resistance, which is either RT or REQ. You'll just have to get used to that. All right, thanks for listening, guys. Take some notes. Try out some practice with the parallel circuit, too, to make sure that you're doing okay with it. Thanks for listening.